Yes, and recording. Okay, so we started our webinar with recording with such things. And first of all, I want to repeat, I finished some work with Numerical Integration Lab and with Final Project Lab. So first of all, of course, I shifted the deadline for Numerical Integration Lab. Now, new deadline is 19th of June. So it's not 12 June as it was earlier. So right now you can find this Numerical Integration Lab. You can press this button and you will download some file with lab. So here you can find, oh, maybe you can't see what, maybe you haven't seen the opened one folder. So 1 second please. So you can press Numerical Integration Lab right now. You can, no, I allow you to download. So you can download this zip archive. You can find here, first of all, you can find pictures, the pictures that were supposed to be seen by you for this lab. And here you can find two files, lab fixed and lab pure. So lab pure is a file with lab that how it looked on the Coursera, and lab fixed is such lab, but I added some details. First of all, I blended CheckerPy and lab pure. So now you can lab fixed looked like this. Here you can find the CheckerPy file, the file from CheckerPy, and first of all I just ask you to run this cell. First of all, that's your first task, just to run this cell. So all the material from CheckerPy will be available right now, and after that you can work with your lab. Unfortunately, there is a little problem such that how you can see with the images, because you need some complicated work to make them visible. But here you can see that sometimes you will see some nodes like this thing, like this thing, or like this thing, and you'll be able to see the pictures. As you can see in the folder, in this folder, you can find the corresponding pictures. Like for example, here you can find the file 2, or you can see that that notebook is looking for res.png, and you can find like here res.png, and at least you'll have a possibility to understand what this file is looking for. Maybe I will fix it a little more. Maybe I will make some available archive in the internet, and I will add the links to the corresponding files, and so that these pictures will be available right here in the code. But right now, unfortunately, we have no such feature. But at least you have possibility to manage what pictures what pictures do you need. So right now you have this new lab. You have a deadline like 19th June for this lab, and 19th of June for this lab. The same story with Final Project Lab. So what was the necessary introduction, as I think. So I think that will be really useful. Okay, I'm ready to answer your questions or to discuss some things you want to discuss. So if you have something, well, let's start small talk about it. I suppose what you want to talk about this lab, maybe we can have a brief introduction into this lab. So, but I'm waiting for your reactions.
let's discuss labs. I think it's extremely useful.
Okay. If we do we have any other suggestions? Okay, it looks like it's a key idea. So I think what you have started with FIFIC. So you know what the key idea of integration. What does it mean? But we know what. For example, you know that when we talk about the definite integrals, when we are talking about the area under the curve, like I prefer to say that we are talking about oriented area under the curve because as you know, but we have some segment of positiveness of function, we have some segment of negativeness, if one can say positiveness and negativeness. Like we know that area under the curve is not very good term because word, because if you are looking for the integral of function f from a to b, when you need to compute v square and definite integral of function f equals to s1 minus sb s2, because square area is always positive. So formally, this when we talk about areas, this is positive value, like positive size of the figure, and this thing is positive too. But so that's why I like to talk about oriented area, because we have positive area and this area is negative. Okay, so and as you can imagine, sometimes it's really hard to compute the proper integral, some theoretical value of the integral. Sometimes we're interested in computation of using of numerical methods for integration. For example, as it was with numerical differentiation. So now we have some simple ideas about the way of computing of integrals. So let's start with let's discuss three simple ideas of numerical methods for integration. For example, first of all, we want to discuss the idea of midpoint rule and of rectangle rule, as one can say. We have a following idea. But suppose the following. But we have some function, this is interesting function, like this one. And we want to compute the area under the curve. So how can we do it? Okay, maybe we are lucky guys and maybe we can compute we can compute a definite integral from a to b. But as you can imagine, it's hard to believe that we are such lucky guys, because lots of functions in the world are integrable in elementary functions. So in plenty of possible situations, we have no possibility to compute the definite integral theoretically, but we can do it numerically. So how? For example, we can split this into this diapason, this segment, make a partition like it was in numerical differentiation lab. We can do something like this. I don't want to finish this process. And we can say the following thing. How one can compute numerically the area of this part of the under the curve, like this part. The simplest idea is to do the following thing. Let's have a look. We can say that we can take some random point from this segment, some random point, for example this one. We can compute the value of the function at this point, for example this one, and we can multiply the value of the function at this point to the on the length of the segment, like as you can see. So we can multiply x1 minus a or we can rename it at give it simple name like x0. So we can say that the area and the curve is close to the area of this rectangle. Okay? Plus, minus, you can type it in the chat. So, as you know, I'm a plus minus dependent guy, so I need your reaction to be sure that everything is okay. So we can compute plenty of such rectangles like this one. You can imagine this plot isn't very good, like, because it's hard to build a good plot. Like, and we can say that these rectangles are pretty good approximate the real area and the curve. So the idea is to take if one can take really great number of points, when one will achieve really good approximation for the area under the curve. So it can be a good approximation of a definite integral of this function. So that's nice. I think that that's an easy idea. So let's talk about so that's the key idea of integration. So now we want to talk about the so what do we need to talk about if we are talking about the concrete numerical methods? First of all, is in this idea, in this logic, we have lots of how to say, степень свободы, lots of freedom in this model. We have lots of freedom in this model. First of all, the simplest question here is how to choose the point. How to choose the point so that we will take degrees of freedom. Yes, thank you, because sometimes really simple words are twisted out of my mind, and like degrees, I couldn't remember this word. Yes, thank you. So, the simplest question is how to choose a good point for computing of to compute the value of function. So, what's the simplest idea? What can you say? What's the simplest idea of how to choose the point?
Maybe some mean value.
A mean
Or
value.
some way
Yes, for example, the simplest idea is to take the center of this segment. So we can take
Yeah.
we can take the center of this segment, or we can take mean of value here and here on the oh my god, on the borders of this segment. Yes, there's lots of simple ideas, but we suggest you to do the following thing. To use the method of the center point. Like, we suggest you to write a function, such that approximate the value of definite integral, like length of with choosing of the center of every segment. Like here we take center, here we take center, here we take center, and we build the corresponding we build the corresponding rectangles, and we approximate the value, the total area, like using this method. So here you can find an appropriate corresponding formula. We can say that in this setting, using this name of values, t points are such points that we compute the value of function at them. So the first idea is to take ti as xy minus 1 plus xy, their mean. We can take their mean. So in this setting, if we take a uniform partition of a segment, like distance between all the xy and xy minus 1 is the same value, like h, like some value of step. So we can easily say that if we split our segment from A to B with n points, so so h parameter will be equal to b minus a over n. So it's easy. It's easy to understand. And we just need to multiply it on the sum of function computed at center of your the centers of your segments. Okay, that's nice. Do I need to add any explanations? Okay. Plus minuses logic is wonderful. It was one of the best pedagogical inventions in my life when I understood that I can ask students to press pluses and minuses. So it simplified my life many times. Okay, so the task number two gives us in the task number 2 we ask you to plot the result, like what's the number, res png. So we can see that we ask you to try to build something like this image. I think you can see it using command plt point bar. So we suggest you to read a little about it, or maybe you can ask our unbelievable cool assistant Azamat in chat. Or as you can see, he's unbelievable. So it was a great luck that he was enough free to join the course. So okay, we'll ask you to build a plot, like to build a real curve that corresponds to your function, and also to build rectangles that corresponds to your to the rectangle from this method. So function plt bar will help you to do it. Okay, so also, but we have another idea. So we had an idea with mean values, using the means of using the average value of the function at the borders. So what do I mean? We can build another figures, not only rectangles, but we can use in the task number 3. We suggest you to use trapezoidal rule. What's the idea of the trapezoidal rule? We come with where is the it's another simple idea. Sorry, I'm a bit ill. That's why I mumble a little. So maybe I hope it's not a big problem. We can do the following thing. We can approximate our truthful area under the curve, or our truthful definite integral, using the average value between functions of the using the average of the values of functions at the borders. So we have a following idea. We can split with the same logic, like we have some amount, and we take or we have some amount of points, and we build a uniform partition of the segment. Yes, but now we multiply the length of the segment on the average between fxy minus 1 and fxy. So as you can see, it corresponds to the following idea. We can take something like this line that passes through this point and through this point, and we want to approximate the value of your integral of your area using such trapezoidal. As you can see, it this logic can approximate the real value of area under the curve. Very good too. So I don't know what to add. So, and we suggest you to use this rule. That's easy. The most complicated rule is well known. is as a Simpson rule. So this logic is more accurate when in comparison with the previous one techniques, and it gives us an approximation using parabolas approximation. So when we use Simpson's rule, we don't want to use such approximation like it was. We don't want to use linear approximation as it was done in the previous examples. But we can do the following thing. We can try to build a parabola that passes through points, through three points. Like, it won't be very beautiful, but you can imagine. That's the first one parabola. Like, I don't know how to draw it, so I hope you will understand me. Like, and that's the second one parabola for the segment from x2 to x4. I understand that it's hard to see what we think is parabola, so I will leave you some hints. It's like when it looks like I'm drawing I don't know, sheep, and I ask you to believe that it's a cow. So, but maybe you will be kind, but you will understand me. Okay. So that's for task number 5 or for task number 4. We need some we need some imagination. So what we can believe that this function is so what do you believe that these curves are parts of the parabolas So the idea is the following: that you can split your point with but you can make the same partition as usual, but now you want to say that you need to write this formula. You need to use this formula to make an approximation for the on the segment which includes 3 points. Okay? Do you have any questions? Why 3 points? Because parabola consists of 3 parameters, as you know. Parabola is some things. So you need 3 points. Yes. To to fix all of them. Okay. That's great. So, and you have a concrete formula so you can so we just want you to code this formula, as you can imagine. Please be careful with odds and evens, or odd and even amount of points in your partition, but maybe it will be really useful to have a look on it. Okay, so we have this Simpson's rule. Okay, maybe it's kind of strange. Maybe it's a little strange thing that we have 3 different rules. So maybe some of them are better, maybe some of them are worse than others. So and using this table, you can see that Simpson's rule is much more accurate in comparison with 2 previous ones. As you can see, here we can see what is the size of the error for middle point rule. you can see that it's proportional to b minus a in cube over n in square, and with some constant like 24 in the denominator, and maximum of modular of second derivative in a Saletel. So, do you understand this formula? It looks a bit strange, but I think you understand that b minus a is taken. Do you understand what does it mean with max a b f in square, f second derivative modular?
Could you please comment on this max on the interval? I don't know.
Okay. So let's look on some example. Like, let's take some function. Like, what's the most simple function of all? Sinus. Okay, fx is like sinus x, and we want to compute something. We want to estimate the error of your. Want to estimate your error of a middle point rule. Yes. And we know that estimation. And we have some segment like A, B. But imagine, consider the following: we want to compute the numerical approximation of this function on this segment using middle point rule. We have a possibility to estimate the size of the error, like b minus a over 24 n in square, the size in cube, multiplied on c, and c is a max of second derivative of your function. Like, we have, of course, if your function is a constant, for example, when you will have a zero approximation, a zero error approximation, because your function is simple. So, as you can see, all the troubles with these approximations happens when your function changes its value really fast. Like, if it's something like this, like you can imagine, if it's something like this, it's really hard to approximate the value of the area under the curve properly. So the correctness of the approximation depends on the speed of change of the function. So here you can see that error can be theoretically bound with your knowledge about the second derivative. For example, in our case, what can we say about if a is 0, b is 5, function f is sine x? What can we say about the maxima of second derivative of f, of modular of second derivative of f on this segment? What can you say about it?
It's minus sine of 0 is 0, then maybe it's minus sine of b.
Minus sine of b. So I think that
Like first you have a sine and the second is minus sine.
Yes, I agree.
And yeah, and we have 0 and 5. And so sine of 0, as we know, is 0. Maybe something where sine equals 1.
But I think it's you can just
Yeah, just remember this number. Okay.
you know the sine of
divided
p over 2 is 1. So here you can, for example, you can get minus sinus x, and you can take point. You know what this value is bounded. 5. Well, you know what this value of sine x is bounded between minus 1 and 1. Yes. So you know that you can take, for example, p over 2. You'll get minus 1, but you have modular, so it will be 1. So you know that maxima is 1. Okay?
Just one question: if we have something not sine but some more complicated derivative, we just have to calculate some series of numbers, or how to do it?
That's an open question. So sometimes usually it depends on the function. Usually you have usually you work with differentiable functions, because indifferentiable functions are really complicated. So usually you have differentiable functions, and usually you can estimate the size of a second derivative. Right now it can be done really easily, but usually you'll have possibility to approximate the value of a second derivative. Okay? At least yes, at least in our labs. So here we can easily say that our size of our error is bounded with a5 in cube, 24n in square multiplied on 1. So you can easily say, so the size of your error can be bounded with this value. So if you want to have error, for example, less than this value, then you can just find such n that this inequality holds. Just for example, some. Yes, it's a number of points you use. Formally you use n plus 1 points. Yes, and n is number of intervals. So one can say that it's something like this. This is approximately 5, as you can see. Like it's okay, that's less than 6. So you can just do something. So everything is okay, or no? Maybe it looks like I need to put it. As usual, I messed the positions. So if you want to bound your value with the size of your arrow with this number, you can just find. You can look for. You can search for such n, but this inequality will hold. So this inequality is always correct. So you can just do it as you can imagine. Okay? Nice. So you can take some good enough n and you will get some bound. Like you can take n that equals to 100 and it will be enough. So, okay. And you can be sure that your error will be less than 1/100. So, okay. So here you can see that middle point and trapezoidal rules are kind of the same. They have the same bounds for your error. Like the difference in they have differences 2 times, so it means nothing in our situation. Where both of them are proportional to the cube of the length of the segment. Both of them are proportional to the maximum of the modulo of the second derivative. And Simpson's rule is much better because it's proportional to n in 4th degree, as you can see. So adding when you add more points, Simpson's rule converges much faster than middle point or trapezoidal rule. But also it's important to note that it's proportional to the maximum of the 4th derivative, of the modulo of the 4th derivative. So what do you think? Can it be a problem? Can it make our situation even worse when proportionality to the second derivative? What do you think?
Yes, because we can have some discontinuity in further derivatives and maybe.
For example, maybe you have some maybe you have a function that have two or three derivatives, but don't have four derivatives. So this rule will be applicable to a function, but these rules will be applicable. Okay, so task number 5 is dedicated to your so what happens here? Wait, 1 second, please. Okay. The task number okay, task number 5 is dedicated to to the checking of correctness of your computation. Like as you can see, we can have a following situation. We suggest you to take a concrete segment and concrete number of size of partitions, amount of points in your partition, and we suggest you to iterate through set of values of a parameter, and so we suggest you to compute the first of all, we suggest you to compute the correct value, where pure theoretical value of sorry, that was a mistake. We suggest you to compute the theoretical value of this integral. I think that you understand that this value can be easily computed analytically, the concrete value of integral. Okay? And after that, we suggest you to compute a trapezoidal rule approximation with using all these values of parameters. And we suggest you to how to say, please thanks me, сравнить, how to compare. Thank you. As I've already said, I'm a little ill, so sometimes it's really hard to say these words in Russian. So in English too, extremely. So we suggest you to compute. No, we don't ask you to build 7 graphs. We just you can build one graph with 7 beans, like 7 segments. And to dedicate to compare the size of error for this value of parameter a, for this value, for this value, for this value. It will look like, for me, it's gonna look like, I don't know, like, so no, 1, 2. I don't know, so something like this one. Like, so here you can see the values of A, and here you will see the values of error. Okay? So that's great. And the last task is dedicated to comparing of all three methods. Like, we suggest you to take a concrete function, concrete segment again, to compute it analytically again, and after that we suggest you to compute the numerical values of integral with all three methods for all the possible values of n, all the given values of n, and to estimate and to compute the error between analytical value of the integral and between middle points rule for n equals 10. To compute the error, to compute the difference between analytical value and between trapezoidal one computed with n that equals 10. The same thing with Simpson's rule for with n equals 10. And to repeat the same thing with all the given values of n. And we ask you just to visualize like your results, like how it looks like, what can we say about it, how many to build a graph with the same logic as it was here, like, but you will have 3 lines. Like imagine that that you'll have something like I don't know, like 10, 50, 100, and you will have something like this. I don't know, it's just you will have something like this for middle point rule. Oh, well, people still want to join us. And you will have, and maybe you will have something like this one. I don't know. I can't. I have no. I have no skill in drawing, as you can see. And this one for Simpson rule. Of course, we expect a lower mistake for Simpson's rule in comparison with middle point and trapezoidal one. Okay. So that's nice. And the last thing we can mention is task number 7. We ask you to discuss a little some theoretical results. What do we think about the best method for the function x in power of x? What do we know about what's the specifics of approximations for e in power ax and such things? But I don't want to discuss these questions because you need to work a little with your own hands before you will understand what's the idea of these questions, I think. So that's it. So I think that we have discussed with lab, and maybe it will be much more easier for you to finish it. This lab is even easier than numerical differentiation lab, I think. But the last one is a much more complicated one. So maybe all the following webinar we will dedicate to the final project lab. Well, any more questions?
Yeah, just to clarify, not about integrals, just to clarify here, in the extra for week number 4, we have a question about function x, or you can open it maybe. Just 1 moment. So it was like for when it has it seems like it has equal partial derivatives in the point 0, 0, but if we just paste x is a function of t and y is a function of t, so we have another value and chain rule doesn't work. So my idea is just to say that at the point 0 it's not differentiable.
I think it's not very good to discuss it right now, right here, because it's not even finished. So maybe if you have some concrete questions, you can write me in the messages and we can talk about it, for example.
Okay, thank you. I'll write it then.
I think it's not a proper place and proper time.
Okay.
1 second, I will turn on the light. because as you can see, it's just time, so it's just an hour, such that the sun disappears from the horizon and it turns into the darkness. Okay. Any questions?
I just have no questions because I only trying to understand what about that lab that you understood that you what you explained was very clear, but when I will start to do lab, how can I ask questions about it in Telegram channel?
Yes, for example, in Telegram channel, you can ask, you can write in direct messages to me. You can write in direct messages to Azamat. So I think we will find the way to to help you with your lab if you have some technical questions. Maybe
Thanks.
maybe even I'll find some extra time. Maybe we will if there are plenty of students who have technical issues, maybe we'll find some time and we will provide extra webinar in my spare time, maybe even in Russian, just to simplify the situation for the students.
That's very
for the-
will be very useful. Thanks.
So if you're not the only guy who has such issues, so when you can organize you and your colleagues, so maybe it will force me to organize some webinar to dedicate some time to you, all of you.
Okay, good. Thanks.
Great. Okay, any questions? Well, it looks like you have. If it looks like you have none. So, as usual, I prefer to talk about interesting, simple, or maybe not simple, interesting things. Like in the previous time, we discussed some as a part of extramaterial such function that has differentiability only at one point. Questions will be later. Okay, I understand you. So. Of course, we can discuss some interesting example of some interesting question dedicated to integrability, but I'm not sure that we have enough time, that we have enough knowledge. Maybe you have some questions about the basics of integration. I don't know. So let's talk a little about the basics of integration. So what's the key idea? Because we have we need to know two important things about integrability. Usually when we talk about integrability, we can talk about two really close but a bit different things. So first of all, indefinite integral and definite integral. What's the difference? The indefinite integral is a set of indefinite integral of some function f, so like indefinite integral of some function f is a set of functions such that their derivative equals to f little. Like here you have fx, and when you draw this symbol, like symbol of integral without limits, a lower bound and upper bound. When you build set of functions, such that for every function, formally you build set of functions f such that their derivative equals to your equals to your function inside the integral. Okay? For example, what can you say about this integral of this function? What's the integral of 2x? Well, one can say that it's x in square, because the derivative of x in square, yes, is 2x. But this, that's a bit incorrect answer, because formal answer is x in square plus constant. Because for every function of this form, you know that its derivative equal to x. Okay? So, and first block, as you can see, is dedicated to indefinite integrals, about techniques of computation and about the key ideas, how to do it. The second the second topic is definite integral. What is it? Consider the following. We have some function fx, and now we want to compute definite integral of this function. The result will be number. So what corresponds to the, in some informal way, that corresponds to area under the curve. So that's why we were talking about the area under the curve. Formally, the to be honest, informally, the indefinite integral of function f from a to b equals to the area under the curve. Okay. So, what's the link? Why do we use the same word like integral for this construction, Because we have a theorem named like FTC, like Fundamental Theorem of Calculus. It tells us that if you know that big F is anti-derivative of f little, so what means antiderivative means that the derivative of your big F equals to f little. Yes. If you know that, or formally, if f belongs to the set of indefinite integral of f little, when if you want to compute the definite integral, then you can compute the difference between values of your antiderivative at the b point and at the a point. So this thing is named the Fundamental Theorem of Calculus, which gives us the possibility to compute the area under the curve using some strange technique of integration, like of computing of antiderivative. So that's the key idea of integration. So the main goal is usually to compute the area under the curve. So that's why our numerical integration lab is dedicated to the idea of how to compute the area under the curve, if it can be done theoretically. For example, because this theorem gives us an analytical way, but as you know, it's easy to compute the derivative. Usually, you can easily compute the derivative of the function, but sometimes it's just impossible to compute the integral, an indefinite integral of function. For example, we can take Wolfram alpha, and we can ask him to compute something like some integral like I don't know, like x in square multiplied of sine x. So let's ask him to compute it. So look, it can be easily done. He can compute. It can compute with antiderivative. It gives you a indefinite integral. But what will happen if the one, for example me, will ask him to compute the integral of e of exponent in x and square. As you can see, it doesn't give you some simple and short answer. It gives you something strange, like, because the integral of this function can't be computed analytically. You just need some specific function named as Rphi. Yes, you need some specific function to write the value of this integral. Like formally, here you can see that integral of e in the power of x in square is some constant multiplied on specific antiderivative of e in the power of x in square. So it's like that's a good example from the book of Kir Bulichov. Maybe you know this author. He wrote a lot about the Alisa. And there was a good example, like, а что такое экспонат? А это то, что экспонируется. So that's the same thing happens here, like, what's the integral of this function? Is a specific function that gives you an indefinite integral of this function. So sometimes it's really hard to compute the antiderivative. So sometimes fundamental theorem of calculus can be used. So sometimes we need numerical methods to integrate. So that's the key idea of the lab, to give you some knowledge about numerical methods of computation of indefinite integrals. A couple of words about it. You know what? It's a bit hard to say something because it's a very big topic. So it's a huge, tremendous topic. So on this course we just will have a look on idea of numerical of multivariate integrals. Like sometimes you want to compute, you have function of several arguments, like multivariate functions. Like, for example, you have function like this one, and imagine, and you know, but sometimes we are interested, I don't know, in some, for example, in some volume of a figure built by this, given by this equation. So, for example, sometimes we are interested in computation of double integrals. Like sometimes we want to compute something of this thing. For example, one can compute something like this construction, like it's the simple. That's the simplest case of multivariate integrals. Sometimes you're interested in computation one by one of several integrals from one function. Like here, we ask, for example, in this example, I suggest you first of all to compute this integral using y as parameter. Like it's not a in the case with computation of partial derivatives. Here we think that y is a constant. We don't want to work with it, and we can easily, for example, put it outside the integral here. And now, for example, you can compute the value of this integral, and maybe, after that you can compute the value of external integral. Sometimes life tends to be can be a little more tricky, and sometimes your boundaries can sometimes your boundaries depends on your own external variable. For example, here you can see that we can take y outside the integral, but now you can see that the value of this integral equals to e in y minus 1, because that's e in 0. So, and now you can compute another integral, more complicated one. So what's the basics of multivariate integrals? Maybe it will be useful. we talking about? Something about multivariate functions. Oh, okay, just ping me in Duke messages. About set of functions, when we talk about the indefinite integral, formally we are searching for the set of functions. So, indefinite integral of 2x is a set of all functions of this form, because every function of the form x squared plus const gives you 2x after the differentiation. Okay? Well,
Because constant c may be any.
yes. For example, you know that you can take x squared plus this number. What do you know about the derivative of this function? What do you know about it? What's the derivative of fx? You know that it equals to 2x. Of course, you can take fx that equals to x squared minus square t of p over arc sin of this number. So still the derivative of this function equals to 2x. So it doesn't make sense. What const do you use? Okay?
Okay.
So I think it's time to finish our webinar. I hope it will be. I hope it was useful. So see you next week. And if you have great set of numbers of questions, you can organize some group of students. You can ask me, and we'll find some hour maybe outside the outside our course and outside my working time, and we will talk in Russian about your issues.
Thank you.
Not at all. Well, see you next week. Goodbye.